Today we're going to talk about implicit differentiation FRQs and the common types of questions you see associated with these types of FRQs. So similar to our previous videos, I'm going to start with an overview of the main kind of areas of content that you're going to need to know to be successful in these types of questions. So the first thing is finding the derivative implicitly. Okay, that's something you should know how to do. But more specifically, finding the derivative implicitly of the following expression. That's x times y. So if I want to take the derivative of this, recognize that it's going to be implicit differentiation first because we have an x and a y kind of together, and also we have to use the product rule of differentiation here. And so the derivative of this, using the product rule implicitly, is the derivative of x, which is 1, times y, plus the original first function x times the derivative of y, which is dy dx. Okay, so that's an important thing you're going to need to know. This concept right here shows up in most of these types of FRQs. Okay, the second thing is finding second derivative by plugging in the first derivative. So a lot of the times when you want to find f double prime or the second derivative of y with respect to x, you're going to have that derivative in terms of the first derivative. And then to evaluate the second derivative, you actually have to plug in the values of the first derivative. And you're going to see that in part C for FRQ number 1 today. Okay, next common question you're going to see is finding the horizontal / vertical tangents. Okay, horizontal tangents, you should know that you are setting a lot of times we're going to be dealing with fractions, so you're going to set the numerator of the fraction equal to 0, because if the numerator of the fraction is equal to 0, then the entire fraction is equal to 0. And if the derivative is equal to 0, then it's a horizontal tangent. So you're setting the numerator of the derivative equal to 0 to find the horizontal tangent. For the vertical tangent, you're setting the denominator of the derivative equal to 0. And that will give you an undefined result, which represents a vertical tangent. Okay, and then lastly, before we start our first question here, finding the tangent lines. Okay, the tangent line, the general form is y minus y1 equals m times x minus x1. And so this is the general equation you're going to have to use to find the equation of a tangent line. So you need a coordinate point that is represented by x1 and y1, and then you need the slope or the value of the derivative at that coordinate point. So like 3 things in order to find the equation of a tangent line. Okay, so that's the basic overview of implicit differentiation. Let's get started with our first FRQ. Okay, FRQ number 1. So here we're given an implicit equation. It is an implicit equation because the x's and the y's are kind of jumbled together. And we are also given the derivative of this equation, which is nice. Here's the equation, and over here is the derivative. The first thing we want to do here is determine the equation of the tangent line at -1, 1. So from our notes, we know that the equation of a tangent line can be found through this equation, where x1 and y1 are coordinate points. Those are going to be given to us for this first question, and then the slope m is going to be found through the derivative. So to determine the value of m, what we're going to do is evaluate the derivative at the point -1, 1. So we're going to take the derivative over here, and we're going to plug in -1 for x and then 1 for y. So 3 times 1 squared minus -1. Okay, and then if we evaluate this, we get 1 over 3 minus -1, which is 3 plus 1, so it's 1/4. Okay, now we can plug everything into this equation. So y minus 1 equals 1/4, x minus -1 or x plus 1. And then if you wanted to, you can kind of solve this for y. And I'll just leave our answer like this. So that's our answer for this one. Second question wants us to find the coordinates where the tangent line is vertical. So to do that, we're going to start with the derivative here. Then if you remember from our notes, the tangent line will be vertical when the slope of the derivative is undefined. And to do that, we're going to set the denominator here, this denominator, equal to 0. So 3 times y squared minus x equals 0. Okay, the problem here though is we have two unknowns in one equation. Let's solve this for x. Okay, and ultimately we want to find a coordinate pair of x and y that satisfies this equation. But the problem is we only have one equation. So we need a second equation. And that's where this is going to come into play. We're going to use the original equation to solve for, to make one equation with one unknown. Okay, so we've already solved for x here. So what we can do is take this x value, and we're going to plug it into the original equation. So we get, this is y cubed minus, let's write 3y squared instead of x times y equals 2. So this right here is the original equation. And now let's simplify this and see if we can solve for y. So y cubed minus 3y cubed equals 2. We have negative 2y cubed equals 2. So y cubed equals -1. And so y is equal to -1. -1 times -1 is 1 times -1 is -1. So now to get the x value, we're going to take this and plug it into this equation right here. And let's solve for x. And this will be the coordinate pair that makes the denominator of the derivative equal to 0. So if we plug it into the derivative, we get 3 -1 squared minus x equals 0. And so we have 3 minus x equals 0, and so the x value here is equal to 3, which means the coordinate pair, our answer, is going to be 3, -1. And this right here is the coordinate pair that makes the denominator of the derivative equal to 0, therefore makes the tangent line a vertical line. Okay, and that's the answer for part B. Now to wrap up this question, we're going to evaluate the second derivative at x equals -1 and y equals 1. So part B. To find the second derivative, let's start with the derivative. We know the derivative is, let me just rewrite it, y over 3y squared minus x. Yeah. Okay. So now to find the derivative of this, we're finding the derivative of the ratio of two functions. And so because of that, or the quotient of two functions, because of that, we're going to use the quotient rule. So the second derivative is going to be equal to low d high, the derivative of y is dy dx, minus high d low, so it's 6y dy dx. Derivative of minus x is -1 all over 3y squared minus x squared. Okay, and so let's evaluate this at the coordinate point, -1, 1. So we're going to plug in 1 for y, so 3 minus negative 1, so 3 plus 1. The value of the first derivative, what we can do is plug in negative 1, comma 1, but we actually already did that. And so this is the value of the first derivative at negative 1, comma 1. And so that's what we're going to plug in. Whenever we see dy dx, here we're just going to plug in 1/4. Minus 1 times, well, 6 times 1 times dy dx is 6 times 1/4 minus 1 all over 3 minus negative 1, so 3 plus 1 squared. Okay, now let's see if we can simplify this. So we get 4 times 1/4, that's 1, minus, this is really 3 over 2 minus 1, which is 1/2, so this becomes 1 minus 1/2 over in the numerator, and then the denominator becomes 4 squared, which is 16. Well, 1 minus 1/2 is 1/2 over 16, and so this is the same thing as 1/2 times 1 over 16, which is 1 over 32. That's going to be the answer for part C. I'll make this one in red as well. So that's the answer for part C of this FRQ. Okay, for the second FRQ in this video, we're given an implicit equation. I'll rewrite it here. We're going to start this question by, we're no longer just given the derivative, we actually need to calculate what the derivative is for this one. So we're going to have to find the derivative of this equation implicitly. And to do that, we're going to use the product rule twice. Once for each one of these terms here. So we're going to have to use the product rule for this term and then the product rule for this term when we're finding the derivative. Okay, so let's start by finding the derivative of the first term here on the left. So we get y squared plus, I'll bring the 2 in the front, 2xy dy dx. So that's the derivative of the first term. Now the derivative of the second term, I'm going to put a minus and then a parentheses, just so it's clear that the negative bit will distribute. We get 3x squared times y plus, we get x cubed dy dx, it's derivative of y, is equal to the derivative of 6, which is 0. Okay, now the negative will distribute to both of these terms here. And so let's rewrite this as y squared plus 2xy dy dx minus 3x squared y minus x cubed dy dx equals 0. Okay, now let's solve for dy dx here by taking all the terms that don't have a dy dx and moving them to the other side of the equation. So that's going to be this term right here and this term. So we have 2xy dy dx minus x cubed dy dx is equal to positive 3x squared times y and then minus y squared. Okay, now let's factor out a dy dx from the left-hand side so we can isolate that term to wrap up this question. So we're going to factor out a dy dx on the left-hand side. The right-hand side will stay the same. And now let's divide by 2xy minus x cubed. So dy dx equals 3x squared times y minus y squared over 2xy minus x cubed. Okay, and let's just let's make sure that matches up with what they want us to have here, and it does. Sometimes the orders might be reversed here. If all of the values are reversed, all you need to do is multiply the expression by -1 over -1, and that will flip the order. Doesn't mean you have the wrong answer, just means it's represented a little bit differently. Okay, so that's letter A. Letter B wants us to find all points on the curve whose coordinate is 1, and then write an equation of the tangent line at each of these points. Okay, so if we want to determine where the coordinate points where the x value is 1, let's take the original function and let's plug in 1 for x. Okay, I'll do that down here. So here's our original function here, not the derivative, just the original. And what we're going to do is plug in 1 for x. Now it looks like we're going to have two y values. That is unfortunate because that means we're going to have to do a little bit more work. Let's find out what those y values are by factoring. So it's going to be minus 3 and then y plus 2 equals 0. So the two y values here are going to be negative 2 and positive 3, which means the two coordinate points that we want to identify the slope and equation of the tangent line for are 1, 3 and 1, negative 2 because the x values are 1. Okay, so let's start with 1, 3. We want to find the equation of the tangent line for this coordinate point. And so we're going to find the derivative, or we're going to evaluate the derivative at this point here. And so to do that, we're going to take the derivative that we just calculated up here, and we're going to plug in 1 for x and then 3 for y into this equation here. And that's going to give us the m value at 1, 3. So what we'll get is 3 times 1 squared times 3 minus 3 squared over 2 times 1 times 3 minus 1. Okay? In the numerator, we get 9 minus 9. And then in the denominator, we get 6 minus 1, or 5. So 0 over 5, that's going to be equal to 0. Okay, well, that means that the slope of the tangent line is 0. So the equation, we'll do that over here, different color. Y minus our y value, which is 3, equals m, 0, times x minus our x value, which is 1. So we end up getting y is equal to 3. So at the coordinate point 1, 3, the tangent line is it's actually a horizontal line at y equals 3. All right, let's do this again for the second coordinate point, 1, negative 2. So let's plug in 1 for x and then negative 2 for y. So 3, 1 squared times negative 2 minus negative 2 squared over 2 times 1 times negative 2, that's our y value, minus 1. So in the numerator we get negative 6 minus 4, that's negative 10. And then negative 4 minus 1, which is negative 5. So we get a value of 2. And so the equation of the tangent line for this one is going to be y plus 2 minus negative 2 equals 2 times x minus 1. Okay, you can leave it like that. Let's just rewrite it and solve for y. So 2x minus 4. And that's going to be our answer for this one. Okay, and let's wrap up this video by going through letter C. So letter C wants us to find the x-coordinate of each point on the curve where the tangent line is vertical. Okay, so how do we find where the tangent line is vertical? Well, we're going to start with the derivative. So 3x squared minus y squared. Oops, times y, not minus y. Over 2xy minus x cubed. And from our notes from the beginning of the video, in order to determine the location where the tangent line is vertical, we're going to take the denominator here, and we are going to set the denominator equal to 0. Okay? So when this statement is true, when this relationship between x and y is true, then the denominator of the derivative will be 0, which means the slope of the tangent line will be a vertical value, or vertical slope. Okay, so let's simplify this a little bit. I'm going to move the x cubed over, and then we could divide by x as well. So x squared is equal to 2y. Well, similar to the last FRQ, we have one equation with two unknowns. So what I'm going to do here is let's solve this for y, and then we're going to plug this into the original equation. Okay, we need a second equation to find the actual value of x and y, so we're going to plug that in up here. I'm going to plug that into the original. So I'm going to plug x squared over 2 in for y over here. Okay, so if we do that, you get x times x squared over 2 minus x cubed times x squared over 2. There should be a squared right here. Equals 6. And so we get, well, it's x squared, so it's x to the 4th times x is x to the 5th over 2 minus x to the 5th over 4 equals 6. Okay? So now if I have a half and I minus a 4th, sorry, I have this reversed. This should be a 4th right here. Sorry about that. Because we're squaring the denominator. So if I have a 4th minus a half, that's going to be negative 1/4. This is negative x to the 5th over 4 equals 6. Okay, almost done. So let's multiply by negative 4. So x to the 5th equals negative 24. And because this is an odd value, because this is an odd number, it's okay that there's a negative on the other side. So the x value is going to be the 5th root of negative 24. And that's actually the answer for this one. So again, because it's an odd value, it's kind of like taking the cube root of negative 1. That's negative 1. It's okay that there's a negative there, as long as the degree of the root is odd. Okay? So that's FRQ number 2. Here's the mark scheme for that. So I'll show you how the points are allocated. Okay, and if you finish with this problem, work through FRQ number 3 on the OneNote.